So it says 1,000 hertz sound and an 8,000 hertz sound each emerge from a loudspeaker through a circular opening whose diameter is 45 centimeters. Assume that the speed of sound in air is 343 meters per second. Find the diffraction angle for each sound. Notice, what is it saying? Which formula should we use? 1 or 2? 2, right? So this is 1, this is 2. So we should use formula number 2, which was sine of theta equals 1.22 lambda over d. So I have been given d, which is 45 centimeters, or 0.45 meters. I have been given a frequency of 1,000 hertz, but I need lambda. So how do I go from frequency to lambda? We know C equals lambda F, and C is just the speed, or I should just say V. V equals lambda F, which is just the speed. So 343 equals lambda F. So we're given 2 of these Fs. So one time plug in 1,000 hertz, and the second time plug in 8,000 hertz. So when you plug in 1,000 hertz, you'll get lambda 1. And when you plug in 8,000 hertz, you'll get lambda 2. Everybody with me so far? Just a matter of plugging those in. And then here also you will have 2 thetas. So it'll be sine theta 1 equals 1.22 lambda 1 over d, and sine of theta 2 equals 1.22 lambda 2 over d. Do we all understand how to get lambda 1? It'll just be 343 divided by 1,000, and it'll be 343 divided by 8,000. I know the answer to the first one, because that's over 1,000, so it'll be 0.343 meters. I don't know the answer to the second one. 0.0. Okay. And can I find theta 1 and theta 2? Go ahead. I'll tell you the answers. I think I got for theta 1, I have about 69 degrees. And for theta 2, I got 6.7 degrees. So I'm going to leave you guys to try doing this on your own. At 6.7. Okay, so diffraction also, again, animals use diffraction a lot to carry their sounds further out. For example, songbirds have very short wavelength, whereas owl hoots are very long. So animals who need sound to travel further out will have low pitched sounds, whereas animals who don't care about their sound traveling further will have high pitched sound. All depends on what is being required. Another very important thing for us to recognize is the fact that our amphitheaters or our rooms are constructed in such a way. I have a very hard time listening to you when you speak, if you're far away. Whereas you do not have a hard time listening to me when I speak, because the way these structures are created is for the sound to carry that way, not necessarily this way. That's why you can speak, you can talk in a theater, right? And the people on the stage will never hear you. But when the people on the stage even whisper, people can hear it. And that has a phenomenon. There's 2 phenomena for this. One is diffraction, and the other one is using destructive interference. Remember we talked about destructive interference? So when you guys speak, the person in the front should not hear it. And let's do a test. So I want you all to come down here, and I'll go over there and I'll speak. And you'll hear the difference. So I will speak with the same voice I'm using right now, and hear me when I'm sitting and then when I'm standing. Tell me which ones you hear. I'm going to stand here and speak. This is the same voice I use when I'm down there. Okay? Now, I'm going to do something else. What if I sit here and speak in the same voice? I'm sitting here speaking in the same voice I was speaking when I was there. You see a difference? Is it louder or lower? Lower. The way these seats are constructed is in fact to avoid the interference that people talking would cause. One more test. I'm going to go further back. I'm going to increase my volume a little bit, and you'll go to the window. Let me go sit here. Okay, I'm talking in the exact same tone that I was talking before. You guys feel the difference? The same tone, the same sound. It doesn't carry. You know why? It's not meant to carry. The way these seats are constructed is it will cause the notes, the frequencies to be dampened. Okay? Now I'm going to try one more thing. I'll go all the way down. And not only because of obstruction, I'll stand here. What difference do you feel? You hear me? How much can you hear me?
A little bit.
A little bit, not much, right? You have a hard time listening to me? Yeah. That is by design, believe it or not. Right? So the voice is meant to carry from you to me when I'm here. It is not meant to carry the other way. Okay, you can all come back. Actually, half of you stay there, half of you come up. The people who are already sitting in the back, can you guys all come up? And some people in the front will talk, and the people in the back will talk. Okay, and I will test it again. Okay, who's talking? So sit on your seats and talk. Feel the difference. That was good. So notice the difference between the men's voices and the girls' voices. Okay, that's what I want you to notice. Okay, girls, say hello.
Hello. Hello.
And now the boys, can you say hello?
Hi.
You see the difference? Men's voices carry further out than women's do. Thank you. And now can you guys say the same thing so they can hear it? Hello or something, whatever you want to.
Hello.
No, one at a time. So girls, we all say it together.
Hello. Hello.
And now the boys.
Hello.
Is there a difference? Right? They seem like they're louder. They're actually not louder. They just seem louder. It's because your voices will carry. Like me standing here, they sounded the same, but it won't carry. And that's diffraction. Woohoo! Perfect. Okay, thank you. Question? No, this is fun, right? Sorry, making you guys all come down and up and extra. Oh, and the other really cool phenomenon, when you think about how sound is produced, is this picture. So if you have a source of sound and you're sitting right in the middle, imagine this is a 3D, you will hear both loud and low sounds. But if you were on the edges here, you will only primarily hear the low frequencies. The high-pitched sounds, they'll be lost to you. So like somebody sitting maybe on that corner outside will not hear anything. They'll only hear the low-pitched sounds. Also, in this room, there is a very particular, I don't know why that happens, but there is a resonance spot right here somewhere. Right here, right here, right here. If I stand here, it echoes. It's a very strange thing. It shouldn't have happened. And there's something wrong with this construction. But there's a resonance spot right here where normally people talking sound really echoey. So I move away from this resonance spot. I'm not doing it. The echo goes away. Right? I haven't moved too much, just 2 steps. Right here. Even if I move like a step down, it has a very big difference. Yeah, that is basically diffraction in work. Right, refraction, diffraction, and reverberation, all of them in work to cause those resonance spots.
I also